Thanks for tuning in to watch the video. Just a note before we get started that if you're ever interested in some one-on-one tutoring, I do offer that service via Google Meet and Zoom classes. So if you're interested, please feel free to drop me a line at this email address and I will provide you with additional information. At this point, you would want to pause the video and reread the problem before listening on. We have drawn a sketch of the scenario. This black dot here would represent the nose of the airplane, which is flying horizontally towards this slope. And we know that the angle of that slope is given in the problem, as well as this height h. And we have to calculate the time that it takes the plane to strike the ground. So the ground in this picture would be right over here. So we're basically trying to find the amount of time it takes to traverse this horizontal distance right here. We might go ahead and just call this delta x. So the question is, how long does it take the plane to travel that distance? And you probably have learned several kinematics formulas in this chapter, and one of those formulas would be as follows. We would have the displacement of the airplane, delta x, equal to its initial velocity multiplied by time plus 1/2 times the acceleration of the airplane times time squared. Now, the acceleration of the airplane is 0 because this airplane is just flying at a nice constant velocity. So since the acceleration is 0, that last term can actually drop out of the formula. So we can get rid of that, and then we're going to solve for the time by dividing both sides by the velocity of the airplane. So this would be the expression for the time. We know the velocity of the airplane. It's given. It's traveling at 1,300 kilometers per hour. So really the only thing that is left for us to determine is the horizontal distance delta x. And if we see from this picture, we note that the delta x would be the same distance here. So you would want to focus your attention on this right triangle that's formed in the diagram and then apply a trigonometric equation. And the relevant expression here would be the tangent, because the tangent of that angle theta would equal the side that is opposite of theta, which would be h, the height, divided by the side that is adjacent to theta, which is the delta x. So there, again, we just applied the tangent ratio, which is equal to the opposite side divided by the adjacent. Now, we're trying to solve for delta x. There's a bit of an algebraic trick that I like to use in this scenario. We can take this term on the left side and the delta x on the other side and swap them. So algebraically, it turns out that delta x would be the height divided by the tangent of the angle. Now, both of those pieces of data were given. We do know the height is 35 meters and the angle is the angle is 4.3 degrees. So let's plug those in. So here we see that the delta x is approximately 465.5, why not, meters. Now that's in meters. When we plug that in for delta x, we're going to actually need to be careful because the velocity was given in kilometers per hour. So we would have some inconsistent units there if we plugged in meters for the displacement and then a kilometers per hour for the velocity. So basically what we need to do is change this into kilometers. And of course, we know that 1 kilometer is 1,000 meters. And if we set up a conversion, we basically just divide by 1,000 and we get 0.4655 kilometers. So now we're going to come back to our equation for time that we developed earlier. And we know the time is the delta x, it's the displacement, divided by the 1,300 kilometers per hour. So let's go ahead and calculate that time. And when we do that, we see that the time is rather short. Of course, it's going to be in hours. We have 3.58 times 10 to the negative 4, and that's going to come out in hours, but we probably don't want hours just because it's such a tiny amount of hours. So we're going to do one more conversion. Perhaps we all know that 1 hour is equivalent to 3,600 seconds. So by multiplying by that conversion factor, the hours cancel each other out, and we are left with about 1.3 seconds. So the pilot has just 1.3 seconds to react, otherwise the nose of that airplane is going to strike the ground.